And welcome back. Next, we have the use of ACVIP containment of the accumulation of program technical debt using AADL implemented on Dassault Systems 3D Experience platform by Dr. Garrett Thurston. Garrett is a senior director for A&D, MBSE, and business architecture at Dassault Systems. He's worked in the aerospace and defense sectors for 35 years, working on and managing Air Force, ONR, DARPA, DOE, and NASA programs, including collaborations with national labs. Welcome, Garrett. All yours.
Thanks a lot. Appreciate it. Today, I took a little change in direction. I added a couple of different concepts. Hopefully, they come off well. I did want to highlight that Brian Chambers is the lead on the governance solutions point of contact if you need to touch base with him on those things, as well as a number of deep dives into different areas that I'll be touching on today. So hopefully we can touch on a few concepts. Previous attribution, a number of folks from Dassault have contributed to areas of this presentation. Basically, we're going to go through a couple of high-level user stories, a little bit on model-based acquisition, extending the concept of technical debt and to contextual debt, a little discussion around latency concepts, and then diving into a little bit of avionics and mission systems, and then touch on some AADL and key takeaways. Here are some basic user stories. Basically, if I'm an acquisition executive, I need to move to improve how I'm going to scale acquisition. As a mission architect, I really want to make sure that from the beginning, we're targeting the right joint effects. And then as a system engineer, I want to make sure that I'm addressing the holistic needs. And so when we talk about mission threat analysis and overarching attributes and that kind of thing, that's what we're really striving to tie these things together. And with the availability of DODI 5000.88 and with the mission engineering guide, we're really starting to change the way acquisition looks at the innovation process. I put these concepts of latency in here to sort of get some idea of that. And Harry Hilliker, time is a dominant parameter here. And so we look at these different things and achieving the outcomes. And so it's a valuable concept to really look at that. I pulled this in. There's been a lot of talk around the sort of warp to the edge concept. And so the arrows down below are saying, let's squeeze that latency across this entire architecture. And then if I look at it, I'm really on the left side, I'm looking at develop and deploy. And I really got to squeeze that need into that deployment to reduce that latency in order to get that solution into the warfighter's need. And that's covered by a different part of acquisition than when I'm looking at operate and employ. And that's where I'm looking there is to take that solution and then use that to better deliver in terms of the O&E, the joint effects. And again, I'm looking to squeeze that latency down and really go after that OODA cycle in order to get inside that adversary's mission cycle. And this WTE leverages the power to the edge concept and obviously the OODA concept in terms of the quality of service and delivering that to the warfighter. So technical debt has to do with sort of not keeping your center of gravity. And so in using something like ACVIP, we're really trying to continually keep our center of gravity so that we understand that we're pulling the right concepts up into the system engineering time frame in order that we don't end up accumulating technical debt. As we look at the vast amount of different assets that we create as we go through the life cycle, we really need to also contain technical debt as we look at looking at families of systems and reuse across those families of systems and the effect of how we're going to manage those assets and where they're used throughout the fleet and where they are in manufacturing and where they are in development. We really have to understand how we're going to manage that contextual debt as well. Here we can see that there's a lot of things going on in terms of containing technical debt, and you can see the process and technology elements related to AADL. In terms of being able to scale acquisition. We look at different acquisition strategies related to the milestone decision authority and the evolving backdrop with the adaptive acquisition framework. And we can see that we're looking to have modular open systems to afford those severable elements that we can redeploy and recombine in different ways. Here is the concept where we have technical debt on the left side, but then on the right side, as we employ these different acquisition strategies, we actually have to address those using things like authoritative source of truth, not multiple sources of data, making sure we have the right kind of traceability for the right configurations going. And then what we're going to get into in a little bit is how we and this is sort of how that ASOT kind of works as we're looking at managing all of those assets to contain that contextual debt. Here's sort of, this is actually taken from DO 326A, and it's the cyber security guidance from the FAA, and it lays out effectively the aircraft and where its vulnerability points are in the typical aircraft, but it also serves as a nice avionics backdrop. And when we look at something like future vertical lift, we'd also be looking at the mission systems. The point that I want to highlight here is we have functional growth as we're going into these increasingly integrated modular avionics versus federated systems. If we had the same growth rate in the critical systems that we have in those aircraft, we would have to start increasing the reliability of those systems, because the more systems we have, the higher probability of failure. And so we really need to tackle that. And the integrated modular approach or phase is very consistent with that. And that's what this slide is trying to reinforce. This is just giving you a high-level overview of what the different sort of swim lanes are as we're going through the process. For the remainder of this talk, I'll really be looking at thinking about the specialty engineering aspects as we look at that from a high-level view. This is the regulatory aspects, and a lot of folks kind of understand the face aspects, but there's a lot of regulatory support for this in the commercial space, including DO 255 and ARINC 653. Here, this sort of breaks out that topology, and that topology has to do with the way we think about the resource allocation problem and how those resources are going to service those functional needs of that aircraft. And then as we're going through developability, how we leverage guidance in terms of recertification of that topology, understanding that DO 297 gives us that ability to go and recertify those concepts. And this kind of ties together some of the concepts that were talked about in earlier talks. We're looking at the notions of how the software starts to be able to be brought into these contexts. And really, we have to appreciate the thinking of the integrated modular avionics with DO 255 and ARINC 653 and the way that DO 297 does that, because this is the super architecture that allows us to really afford to build that functional software and then deploy it around the aircraft to achieve those quality attributes that we really want to achieve. And I know this looks like a little bit noisy, but it really is conveying a simple point, and that is that when we're very early in the life cycle in concept phase, we're really looking at a set of characteristics, a set of abstract things to reason about as we're looking at that system. And then as we move through the life cycle, we translate those into increasingly concrete and increasingly defined concepts. And I like to use the notion of an IRS versus an IDD versus an ICD as we get to detailed design. But this is the same kind of thing that we have to look at when we're looking at specialty engineering in terms of the timing and that kind of thing. So as we move through the life cycle, we actually have to feed back some of that quantitative feedback as we move from tool suite to tool suite, because we're not going to take something like a Cameo, which is a Dassault product, in case people didn't know that, and use that in a detailed design phase. It's not a detailed design tool, and so we need to be able to do that. And that was one of the things I wanted to get across here. So as we go through that process, you kind of got to understand that. the thing that I want to highlight here is that as we're looking at things like mission assurance, we really start to look at things like how are we going to understand what that criticality is, and how do we understand the criticality according to mission, safety, logistics, et cetera, and then understand how we're going to balance that criticality and the principles of functional isolation and principles of separation to achieve things like over here survivability and susceptibility. And if we don't have a way to balance those things, a way to evaluate that, and this is what we do when we're starting to do the mission threads analysis, is we're really looking at architecture trades, things that we're trading off pre-implementation, right? So once we've done implementation, we've really failed to bake in the kinds of things that we want to bake in, like cybersecurity and availability. That really is one of the reasons why we're looking at timing and pulling that up into the architecture as early in the process as we can, so that we can actually have something that when it comes time to do the implementation or the detailed design, we've already know that we've got a formula and an architecture that enables us as neutral toward those quality attributes. So then this is sort of the departure from what I had planned. And so, what I wanted to show here was, we've got this notion of the resource allocation problem. We've got this functionality contained in this CSCI, computer software configuration item. And I put in the A. The A is really to designate a kind of criticality in commercial space. And so I put in that A, and my degrees of freedom in this LRU is to put it in any partition I want, right? But as I add CSCI1, I still have latitude to add another CSCI in that partition. But if I go to add a level B, I'm constrained. I can't add it to the same partition as I have that level A. And now to look at it sort of involving rate, as I look at my architecture and I start to look at the rate, I'm looking at this and I'm saying, well, does this make sense? And I may have constructed this because my thinking at the time of constructing it was either physically motivated or had to do with a particular control system I was working on or something like that. But at some point, I may have to divide up that architecture so it makes more sense in terms of the way I'm going to be consuming my resources, my resource allocation problem. So here, basically, I'm saying I've got CSCI 1A over here, and I got 2A over here, and they have to communicate with each other, but they're communicating at a kilohertz here, right? And so maybe there's something I have to think about in terms of bus loading concerns or functional isolation concerns or principles of separation. If I have something around the aircraft, where I want to have a principle of separation in order to increase survivability, like FADEC on a helicopter, we might separate those so that we have a dual channel FADEC, and by separating them physically, they're less likely to be taken out by a single adversarial round. So here, now we have the challenge where we have CSCI 1A and CSCI 1B. Well, maybe there's a business decision that we might make in this architecture that says, well, we'll apply a higher level of criticality to actually give us more bus bandwidth so that they can communicate in the same partition. So this is basically what I was trying to highlight, in pulling that concept together. So in this case, what I'm looking at here is, so we start out by looking at sort of the mission threads, and we're trying to look at different levels of aggregation as reflected in the mission engineering guide. And we've got some force level concepts, and we want to understand what our latencies and our constraints are in terms of the system of systems at that level. And then as we get down into understanding how everything's going to start to fit together as we start to do our system architecture, in this case represented by the aircraft, and then we start to look at what that mission profile looks like and look at what that system function is. And then as we go into that system safety criticality, then we can start to identify what our particular application software item development assurance is, what the RTOS development assurance is, what the hardware development assurance is. And sort of, there's a trick question I usually give to the MBSE folks around what's the AADL for the RTOS and the hardware and an IMA. The answer is level A. So whereas the application software kind of varies. So one of the things I want to highlight here is when we're looking at the quality attributes that I had in this aspect, it's not going to be an easy engineering task as the number of items increases, the number of communications increase, the number of criticality constraints and the rates increase as we're looking at those things in ACVIP. And so what I want to do is kind of put some concepts on the table in terms of how we might look at this and apply some of the increasingly modern methods to doing this. And I know some of you folks have probably seen this before, but it's equally applicable to MOSA today. And basically, somebody modeled this looking at the physical systems and looking at the interfaces of those physical systems, and had that sort of mindset. And so it has a particular logic to the way this is laid out and assembled. But is it the way that we really want to do this if we looked at balancing all of the physical characteristics or all of the specialty engineering characteristics that we want to have? And we can see we can divide this up different ways. So when we think about MOSA, in this case, you're looking at sort of signals MOSA, but don't forget that all of those characteristics like schedulability and latency are characteristics that we want to look at. So we can actually divide those things up differently and have different numbers of modules with fewer interconnects, and then have the ability to look at modularity in different ways. And just remembering that here we're showing sort of signals, but that's not the only way. And when we scale that up to something of reasonable size, this really is beyond the cognitive ability to just engineer in a solid way. And then if we are failing to really understand the way we want to do modularity in the structure, we may end up having bigger change than we anticipated, because we created an architecture that didn't support modularity and didn't support that change process and that evolution process. And so this is reflecting that. And so the concept here is to use a design structure matrix and to say, well, let's look at how these systems interrelate to each other, be it from the perspective of physical or signals, the communication aspects, or schedulability, or any of those other principles, like principles of physical separation for survivability and susceptibility and that kind of thing. And so this gives you some sense of how that works. And so the idea was, if you can write the right genetic algorithm and conduct some machine learning, and this is pretty sizable, 60 or 61 matrix elements, you really can start to look at how the system might rearrange in order to be able to create something that was more cohesive, more modular, would accommodate change better, would accommodate recompete and avoid vendor lock and that kind of thing. So, and this is just showing you sort of the quality function cost as you go through that restructuring of the modularity of that system. So it's something that really holds a lot of potential as we're looking at scaling acquisition, as we had in that first user story. So then I'll do a little bit of actually not a good idea what time it is here. So okay, it looks like I'm pretty close. So so this is basically saying how the 3D experience platform supports the concept related to AADL. And like I said, there's 3 or 4 other talks that are being given around AADL in the Architecture Collaboration Working Group, and a couple other places that Brian Chambers, who I listed earlier, has scheduled. And so if you look through, what we're doing in the platform is we're taking these concepts and we're building out the functional aspects related to the functional architecture, that hardware architecture, the software allocations and signal allocations in that architecture, and then automatically generating the AADL. And this use case would be during that detailed design phase. So we'd be migrating into that from the Cameo constructs that do it today. So these are the key takeaways, and hopefully that was valuable with some different perspectives that I shifted to this morning. And then these are some contacts. I think that's it. I think that's about the right time, right, Al? All right, Fred?
Yeah, that's perfect. So thank you very much, Garrett. That was great. There are a couple of questions that came in from the audience while you were speaking. The first asks about lots of views and tools. What percentage can be automated and fed and feed each other or fed into each other?
So I think that percentage is probably tough to look at, and certainly there's a slew of applications that get used throughout the life cycle early on in terms of model-based elicitation. Cameo is popular, but not the only one. In terms of doing system engineering, there's a bunch of other applications, the whole MathWorks tool suite for looking at those design elements. Then there's the associated management of those applications that you need to be able to, when you're managing those layers of aggregation in the systems of systems, you really need to not just think about what tools you're using, but how you're tying those tools together, how you're looking at impact, how you're understanding as emerging threats come along, if you can reconfigure to be able to move in that direction, as I talked about the center of gravity, to be able to address that emerging threat and managing that system traceability and the authoritative source of truth so that you can manage whatever tools that you're using. And so, understand sort of the process and how you're going to innovate on that process. And that's one of the things that I tried to highlight in the 5088 is that acquisitions innovating on the way that they're acquiring by putting mission forward. And so thinking there's probably going to be some new tools in that area that allows you to do agent-based considerations that set the policies on the way you're going to do the mission system architectures.
Thank you. I guess to the degree to which that the amount of that integration can be accomplished, you will reduce your technical debt, right? Which is the goal.
Both in terms of the way that you create the validation assets, the integration of the concepts that have been expressed in different tools, and the management of those as they go through the life cycle.
We have another question. You will end up with lots of engineering artifacts, similar to the previous one, but how do you organize your V&V plan to tap into the right subset?
So it's an excellent question, and EAA 632 and ARP 4754 and 15288 all have basically an information ontology that's sort of hidden in there. But the idea is that you would take requirements, either model-centric or model-based or natural language requirements, and you would use initially the right set of applications to be able to validate those requirements. And so you'd manage those in a validation matrix. And then as you move through the life cycle, those validation assets actually serve as the criteria by which the verification is judged, which is post-implementation. So those two information structures that are related to the product breakdown structure of the mission systems and the weapon systems that you're developing are how we manage that information. And it as it goes through the life cycle, or if it's an affected item, or if you're doing product lines, job number one in product lines is how am I going to revalidate that I'm using assets that have the right requirements or have the right parameters on those requirements. And so all of that has to be rigorously managed in the authoritative source of truth in order to be able to rapidly redeploy those in new operating contexts or to do those recompetes that you want to do.
Thank you. I think we have time for one more question, and this has to do with the functional-based approach. that, or functional-based architecture that you presented. There are other architecture frameworks that might be sensor-based or computing-based. Does a DEL architecture make sense, or should it always be functional-based?
I used the functional there only to illustrate that I was going into functional hazard assessment subsequent to that, but that the right architecture views need to be expressed in order to satisfy the right concerns. So when we go into the schedulability aspects, we're going to express something more like an AADL to be able to understand that view, right? And when we go in and do a different part of the architecture, we may do very logical, right? And say this is the logical construct that we've decomposed that to. And so if we look at UAF, it's like Mendelev's table of views in order to make sure that you've satisfied the right concerns with the right model kinds to create the right viewpoints that produce that architecture description. So hopefully everybody got the Mendeleev reference.
Sure. Thank you very much. So at this point, I guess we're going to be concluding this talk. Thank you again, Garrett.
Thank you.
And the next one starts at approximately 1:40. So we'll see you back then. Thank you.
Super. Thanks.